So jumping right in, first I want to clarify that when I'm talking about wind power, this is not the kind that I mean. There's been some confusion in the past. The story really starts with the concept of available potential energy. And what this means is the ocean has layers of water with different densities stacked on top of each other from lightest to the heaviest. And APE is the energy that the system would get when the water horizontally redistributes to a baseline state. What this looks like in the Pacific is that easterly trade winds push water towards warm water to the west, and that pushes the density lines down in the west. Also, cold water upwells in the east, and that pushes the density lines up, giving them that slope that I talked about. Sometimes these trade winds weaken, and that allows the warm water in the west to slosh back to the east and make the east warmer than usual. This also flattens the density lines, which means there's less mass to redistribute, and so that lowers APE. And this is the case with El Nino. And then sometimes the trade winds get stronger, and that pushes even more warm water to the west, and that pushes the density lines deeper and allows even more cold water to upwell in the east. So that makes the eastern Pacific even colder than usual. So this means that there's more mass to redistribute, and that is a higher APE, and that's the case with La Nina. So the focus of my work is on wind power, and this is the source of APE. And what this essentially is the interaction between the surface currents of the ocean and the winds. When the winds and currents work together, it adds energy to the system, and that increases APE, which, as I said, leads to cold SSTs. Likewise, when the winds and currents work against each other, it takes energy out of the system, reducing APE and leading to warm SSTs. So essentially, wind power is a forcing mechanism that can lead changes in SST and hopefully tell us something about SST in the future. What I did was I computed observational results of wind power and correlated it with SST. And this figure is kind of a lot to explain. So what essentially you need to get out of it is that wind power and SST have a strong relationship up to 9 months lead time. And that means that wind power can give us hints about what SST is going to do 9 months in the future. So that's pretty cool, right? We can see the future. Except when we analyze the space-time behavior of the wind power anomalies, we realize that something didn't look quite right. The red things that I circled are the wind power response to westerly wind bursts, which weaken the trade winds. And like I said, that should lead to warming of SSTs. But the red actually means positive wind power, which we said means cold SSTs. So we have a contradiction. And so actually things aren't very cool. As it turns out, the framework that we were originally using to look at SSTs wasn't quite right in the context of El Nino. So my research made a bunch of adjustments to the computation so that it would be consistent. And we got new results that look better and also are more consistent and have a stronger relationship between the two. And so now things are cool again, and it's time to write a paper.